Hi everybody, this video deals with Zener diodes, and before we talk about how the Zener diode is different, we're going to look at back at the diagrams for a regular diode. So the regular diode, looking at the diode curve here, the regular diode can be in one of two scenarios. So we can either have the diode where the voltage falls across it in this direction and it's forward biased, so that's forward, or I'm just going to change my pen size here, wow, or we can have it in this direction, which we would call reverse biased. Okay, so forward and reverse biased. And when the diode is operating in the forward biased mode, it's somewhere along this curve. Okay, it's somewhere along there. Now in the reverse bias region, when we've got a diode in reverse bias, it's somewhere along here, right? So think of your bridge rectifier circuit. When you've got a diode that is off during rectification, it's actually in this reverse bias region here, while the other two of the diodes are there and the other two are here. So it's normal for a diode to sometimes be reverse biased, depending on the operation of your circuit. And so the diode is operating in this region for reverse biased, but notice that we don't go over into this region. Okay, so we don't do that because we don't want to exceed this breakdown voltage of the diode. If we do, the diode is going to start allowing current to flow, and current may even exceed the power rating of the diode, and we may destroy the diode. So either way, we don't want to operate in this part, but we do want to operate in this reverse bias region right here. Okay, so then let's look at the Zener diode. Okay, and that's just more about the two diode states reverse bias we were talking about. So now on to Zener diodes. Looking at the Zener diode, notice the diagram differences. So Zener diode, the bar has these little angles added to the side, and if you turn your head to the left, you can see it kind of makes a Z. Okay, so that's our indication that that this is in fact a Zener diode, not a regular diode. And so let's look at the regions of operation for the Zener diode. So on the left-hand side of this, I have the regular diode graph. So we like to operate here for forward bias and here for reverse bias. Now, for the Zener diode, things are different. So this side is Zener, this side is regular diode. Okay, and for the Zener diode, we actually want to operate in this region, which sounds very strange, but if the Zener diode is put in a reversed biased fashion, so it's actually biased like this, if we can operate in this region, we can have the voltage hold steady at a value that is much larger than the 0.7 volts that we would have over there. So the output across this Zener diode could hold steady at this VZ if we provide a voltage that is bigger than this VZ. So that's interesting. Then we can use this diode to regulate a voltage in our circuit. And that's a very nifty application. So the important thing is when we're doing that we don't exceed this maximum current for the Zener diode. Yes, we want to now operate in this breakdown region where a normal diode wouldn't operate, but there's still a limit to how much current we can put through the Zener diode. So we better have some current limiting resistors in our circuit, and we'd better make sure that we don't exceed this. The rating for VZ that you see on the spec sheet is not actually here at the corner, it's actually here at some test current, right? So the Zener diode will have a particular voltage rating, and there are different diodes with different Zener voltages, so that you can choose the one that fits your application. And of course there's some minimum current that we get when we get over this knee here. Okay, and these values you can find on the spec sheet for your particular Zener diode. Now what you're seeing here is a practical model of the Zener diode that includes a little resistance as well as the VZ. And that resistance can be gotten from this line here, right? Voltage over current as a delta. So that would be a practical model of the Zener. We're going to stick with the ideal model of the Zener for our analysis, but that is something to know. Okay, so how do we analyze circuits with the Zener diode in them? The first thing we do is we imagine the circuit without the Zener diode in it. So we imagine that this Zener diode is not even here, and we ask ourselves, okay, well, what would the voltage be at this point, right? If that voltage is more than the VZ of the Zener, it's going to be limited to the VZ of the Zener. Okay, and this resistor has been added to limit the current. So this slide is just describing what I just said. Let's look at an example here that is going to show us exactly what we were just talking about. So we have a 12 volt Zener, we have a power supply, and we have our current limiting resistor. Okay, the first thing that we are asked is, okay, if we've got 3 volts here, what's the output voltage? Okay, so the first thing we do is imagine the circuit with this gone, and this is open circuit. Now if this is open circuit, there's no path for the current to flow around because the path is broken. So no current is going to flow. If no current flows, the drop across this resistor is going to be 0 because no current is flowing. If there's no drop across the resistor, then the voltage at this point is the same as the voltage at this point, which is 3 volts. Because 3 volts is less than 12 volts, when we imagine the circuit with the Zener back in, this Vout will remain at the 3 volts. Okay, so the answer for this first part is 3 volts. Now, if we up this voltage to 14 volts, what happens then? The first part of the analysis where we remove the Zener and imagine the voltage here is the same, and we'd have no current flow, and this would be 14 volts. Okay. Now, when we put the Zener back in, because 14 is greater than 12, this is actually going to get limited to 12 volts. The Zener will be in that reverse bias region of the curve down here, and current will actually flow in the circuit. So to analyze this, just changing my pen color here, we know that the voltage out then is going to be limited to this 12 volts, and we know that we have 14 volts in. So VO is 12 volts. We want to find IZ. We know that these two components are in series, so it's the same current through both of them. The VR is not zero anymore because current is flowing in this circuit. There will be a drop across that resistor, and you can see if I have 14 volts here and 12 volts on the other side, that VR is in fact 2 volts. So this current, it's IZ because it's going also through the Zener, in this case is going to be VR over R, which is going to be 2 volts divided by 2.2 kilo ohms, and I'm just going to punch that into my calculator, and I'm going to get 0.909 milliamps. Okay, and pay very close attention to your units here. Now the question is, if we add a load resistor, will IZ decrease or increase? So if I add a load resistor here like this, RL, what is going to happen to IZ? Well, just picking a new color here, the drop across this resistor is going to remain the same, so the supply current will actually remain the same. We'll still get the 0.909 milliamps through here, but now that current gets split, some through the Zener, some through RL. Okay, so that means that the current that now goes through the Zener is going to decrease, because before the Zener was getting the whole supply voltage. Now some of it's getting split off to go through the load resistor. And we know that there's 12 volts across that load resistor. That IL would be the 12 volts divided by whatever that load resistor is. The difference between that load current and the supply current, so let me change that to IS now, would be IS minus IL, right? If this is now our IZ. Okay?